Okay, so now it's my pleasure to welcome Frank Hellmann from Potsdam, also in Germany, and he will talk about beyond phase, the dynamics of power grids.
Yes, thank you. Thank you very much for organizing the session and for inviting me to contribute here. Yeah, exactly. I want to talk about going beyond the phase approximation or the phase oscillator approach to power grids that's been so prominent in our community. And we just saw by Rico a wonderful talk about showing how powerful this approach is. So I want to frame a little bit the challenge that I see towards that approach and why I think a new approach is needed. And then I'll work my way towards what we see as sort of a normal form for a more general model of a more realistic model of power grids in the second half of this talk. So, but let me start from the start. So real power grids are not just rotors. They're highly complex, highly heterogeneous systems, certainly high dimensional. We have many nodes, heterogeneous, as I just said. They have the models that are standard used for them have algebraic constraints in them. They're not pure ODEs. We certainly have stochasticity. We have control action in them, which leads to delays and discontinuities. And that's just the existing power grid system. So I've sort of picked out a test system here. So this is really a highly simplified test system that power grid engineers might look at when they study dynamical phenomena or transient stability of power grids. And it's this IEEE 300 bus modified test system containing 69 generators, 306 transmission lines, 174 transformers, and 197 loads. All the generators are equipped with exciters and governors. So this highly simplified model from an engineering perspective already contains all this wealth of complexity from a dynamicist perspective. So we always have to go further than the engineers in simplifying in order to make statements and to also find general principles. And the starting point for this has been certainly to focus on the core dynamics, which we just saw in Rico's talk, perfectly explained. The generators are actually physically rotating masses, they're turbines. So we have a phase of a rotating generator coupled to the power grid, coupled to the through electrical windings to the power grid, transporting energy around. And the focus has been on sort of focusing on these generators as drivers of dynamics. This is certainly where we come from. And then you can sort of think of this in a very analogous way to sort of a phase reduction situation, which is sort of, I think, where a lot of the Kuromoto type dynamical systems thinking comes from. So you smooth out your limit cycle, you look at how the limit cycles at neighbors perturb each other, you put it all together on a network and you get this Kuromoto type equations. And this is sort of our perspective on this. This has been done also completely independently in the power grid community. So in 1981 already, Bergen and Hill wrote down a phase model of power grids, which covered not just the generators actually, because they also introduced a phase model for loads. So, and their goal was to find a formulation to write down Lyapunov functions that guarantee global synchronization, or to understand in what regime we have global synchronization. And we already saw this equation in the last talk, so I don't need to go much into it, but certainly this type of equations have underlied a large range of activity in the last about 10 years from the control theory community, but also from the theoretical physics community, to understand the extreme multi-stability that can occur in these systems, the fluctuation response, optimal parameter choices, rerouting, sort of self-organized dynamics that you can think about here. So, sort of really a vast amount of literature been produced from the control community side, some wonderful proofs about when synchronization is actually guaranteed in these models, sufficient conditions for global or almost global stability of these models. And yeah, as also Rico just already mentioned, we published just a focus issue on in chaos that I've put the link up to on the slide, that gathered a lot of contributions that came about in the last 2 or 3 years in this field. So certainly check that out. In our group, we've been working on this with sort of basically two focuses. The one focus is to numerically study probabilities. So we take this high-dimensional, highly complex system of phase oscillators or what have you, and we ask probability questions like, if I perturb a node of degree 3, what is the probability that I cause desynchronization? These type of probabilities have the advantage that they're easy to evaluate numerically, and we do not make use of the special fact that we have an ODE and phases and so on. So in principle, this type of investigation can be done on the more complicated engineering models. For that, we need to generalize there's a lot of work to actually do that, both on the coding side, simulation side, but also on the conceptual side to define the correct probabilities in this context. But this has been quite successful, and we're still doing this, and we're really excited about working with engineering colleagues now to try to apply this perspective in more and more realistic systems. And what you can do with this is you can find network motives going beyond just counting degrees. You can ask, so what about dead ends? What about triangles in the system and all of these things? And you can certainly study whether the presence of such motives has an impact on the probabilities that you find. And the answer is yes, there are a lot of motives that influence this probability. You can study higher order dynamics, look at line losses, which is exactly how we first found out about this presence of these solitary states, that their probability is much enhanced in the presence of line losses, which had been neglected previously. And you can study certainly control impacts. And then sometimes you get interesting models that are analytically tractable, which we've also looked at in a variety of ways. And this is all work done with a large number of collaborators and students. And in some points here, we already go beyond the phase approach. I mean, certainly the higher order dynamics that were in the physics context first studied by Katrin-Schmiedendorf et al. Already introduced voltage dynamics, went further. When we looked at control impacts or delays, then we're no longer looking at a pure Kuramoto system, but it's still very much in the sort of mindset of this phase oscillators. And I don't believe that's kind of sufficient. Why? I mean, for one, even though these phase oscillators are in some sense very generic, we're really looking at a situation in power grid where we will be facing a much larger heterogeneity of actors in the future than we've had so far. The intuition built on rotors and rotating generators might no longer be applicable in future systems. We already know today that amplitude dynamics are hugely important for actually understanding the physics of power flows, physics of nonlinear instabilities in power grids. And finally, these dynamics that were dominated by phase rotors in the past will be dominated by power electronics in the future. So really, we're also moving to a shift in question, a shift in perspective of asking what type of dynamics, like a control theory question rather, what type of dynamics are stable rather than is the type of dynamics that the machine provides us stable. All of this really leads to proliferation of detailed models. So we, as theoretical physicists, we like the Kuramoto model in part because it captures some key notions of interactions of aspects of the power grid, like inertia, like power flow, imbalance in the power flow, causing a change in the frequency causing a change in power injection. It's sort of like these fundamental aspects of the power flow are captured by it. And these aspects occur in many different concrete models. So many different concrete models can be mapped in some sense, at least approximately, to the phase model. When we want to go beyond that, we don't have that anymore. So we really have, suddenly we face a question of how many detailed, which detailed model should we use? The Schmiedendorf model, the Schiffer control, or Florian Döffler at ETH Zurich has developed several control schemes and so on. So the functional form no longer is fixed for us. And certainly the detailed generator models that have been mostly used so far are not a good guiding principle for what we will see in the future. So based on these worries and based on the idea that we need to push towards more realism in order to really apply our work in real-world power grids, we've been exploring a new way to think about how to model the dynamics and to sort of systematize all the questions that I just briefly mentioned. So the question, so now for the second half of the talk, is somehow, how do we study the dynamics of a future yet to be designed programmable heterogeneous network system? And the answer that we are proposing right now is to start from the physics and the desiderata. And using this approach of physics and desiderata, derive hopefully a reasonable parametrized normal form of power grid actors. And this is work done with Raphael Kogler and also based in part on the insights gained in a bachelor thesis by Hannes Vogel last year. So let's get right to it. What is the physics of power flow in a modern power grid? Modern power grids are three-phase and balanced. So the power lines actually don't have just one sinusoidal wave, but they have three sinusoidal waves. They're phase shifted so that the total sum of the three waves is always zero. That means we can parameterize the three waves by a single complex number, V of t, which automatically will satisfy in the way that I've written on the slide, which will automatically satisfy the constraint above. So note here that this is not like just taking a complex phasor for a sine wave, because both the real part and the complex imaginary part of V of t are physical. Because electrical circuits are linear, the equations that are written in terms of U can easily be written in terms of V, because this is a linear transformation. We have, and the desiderata we want for a good power grid power flow line is to get a steady state. That is, V of t should just rotate with e to the I omega t. We're certainly not the first ones to look at these. We did not come up with these coordinates. They're phasor coordinates in the electrical engineering literature, or dq0 coordinates if you want. Sometimes that's a term that is heard, where d and q are the real and imaginary part of V. And there's certainly a lot of use in the power grid context as well. And we're going to make use of this and to sort of bring maybe a theoretical physics perspective, a dynamicist perspective to this. Given two nodes with these voltages, with these voltage phases, VA and VB, if they're connected by a line, the line will have some inductance and some resistance, and the current that is flowing on the line will satisfy, at least approximately, this equation. In a steady state, we get this type of equation, sort of just a linear relationship between the current and the voltages at the terminals. This is somehow like a complexified version of Ohm's law for AC networks in or near a steady state. And if that means we can express the current on a line in the standard way, and we have the standard sort of Laplacian formulation of a network in this. And this somehow tells us this is really just physics. So we have really just a Laplacian that gives us a current based on the voltages that are applied at the edges. So now to get to the dynamical system, we have to ask the question, how do the voltages at the nodes react to a certain current that they see? So here we have to start inputting more desiderata and more knowledge we have about how the system is designed and what it is designed to achieve. So they only see the total local current and the local voltage. So we have a function of VA and IA. I'm assuming we have active nodes and that their reaction is in some sense smooth. So we have a differential equation here, and we have some internal degrees of freedom at the node maybe that we call X. Now, what do we know? What do we know about the reaction of a node to current and voltage that we can use to restrict the functional form of all of this? We know that there is some symmetry. We want to have a smooth limit cycle. we can look at the invariance under the symmetry to parameterize the system, and then we expand around the desired behavior. So this is going to be the strategy for the next few slides. When I say symmetry, it's exactly as I said before, the limit cycle is e to the I omega t. So I don't want the reaction of my system to depend on where in the limit cycle I am. That means if I translate my functions f and g by some complex phase e to the I phi, I should get covariance for f and invariance for g. This is an additional assumption. We assume that the internal variables are not also co-rotating on the limit cycle, but that the limit cycle is really just a voltage limit cycle. This is this is the first step. Then looking at what are the invariants on this limit cycle, we can make use of invariant quantities, which there are naturally at quadratic order. There are just 4 of, which the obvious ones. And these invariant quantities turn out to have a natural physical interpretation. Of course, VB bar is just the amplitude square of the sine curve. So we have the voltage amplitude as an invariant. But the other 2 quantities, VI bar plus IV bar, so the real part of VI bar and the imaginary part of VI bar, are the power and the reactive power that is injected or extracted at the node. So a well-designed, a well-built node will have these invariants close to a squared p and q. This is something that this system is designed for. Now, out of this 6 quantities we now have, or maybe 8 quantities, vi and these 4 invariants, we can choose 4 to make our coordinates, because we need 4 real valued coordinates here. And these 4 here are a natural choice because near the limit cycle again has v squared or v bar non-singular, and therefore it's a v non-singular. Near the limit cycle, we can express our original coordinates in terms of these invariants in a smooth way. So that is nice. And further, we can, by phase covariance, we know that we have, sorry, I jumped ahead a little bit. Now, as we said before, we want the dynamics of the node of f, of the voltage, to be phase covariant. So the only variable here that transforms under the phase is v. Therefore, we already know that our right-hand side will be linear in v times the function of the invariance. So this is what is written in the first line here. We also know that our internal variables cannot depend on v directly, as there would be no covariant functional form that would satisfy this. Right, so now for f tilde and g, I already told you before that the invariants we have chosen, we know what they should be roughly if the power grid participants are well designed, which is close to a squared, close to p, close to q. So we now can just Taylor expand. And that provides us with a, near the limit cycle, with a functional form that just given in terms of 10 parameters for a power grid participant with the full voltage dynamics and the full coupling completely parameterized. Right. So does this work? So my proposal is that by designing this right, this form here captures the most important nonlinearities. It's up to cubic in the voltage, and we have a nice parameterization with these sort of functional form that we've chosen. I propose it captures the most important nonlinearities. Does it work? Well, so far it seems our first experiment indicate that it works actually quite well, maybe even surprisingly well. So this is this is an inertial version of a dispatchable virtual oscillator control that was suggested by the group of Probe and Dörfler, cited a paper in the bottom. And we've approximated this particular controller design that they proposed in the normal form. And as you can see, there's almost no differences. In the details, there are some very slight differences, but in this particular case, which is some random initial conditions that then run to a particular limit cycle with fixed power injection Q, fixed omega equal to 0. So omega is sort of a differential frequency to design frequency of 50 Hertz. We see that this, the functional form is really quite similar. Now we tried trying different approaches. Here we looked then next at a Drude-controlled version of that can be used maybe in a microgrid as proposed by Johannes Schiff in this excellent paper. And there, if you want to learn a little bit more about sort of physics of microgrids and how control engineers think about that, just an excellent paper to read. And also in here, we see slightly larger differences. So for example, here you see that, do I have a mouse? I have a mouse here. You see that here the curves touch, here they don't quite touch. But this is really, I think, quite excellent. We're really close to the behavior. This is, I mean, in some sense by design, we've expanded around the limit cycle. There are trajectories that run into the limit cycle. And that's it. And I'm not showing the Schmiedendorf et al. Type of voltage dynamics here because the graphs look basically the same as this here. But going a bit further, and I think this is much more interesting, if we look at these...
Frank, we have overall some 2 or 3 minutes left.
I'm okay. I'll be done in a minute. This is like, I'm 2 slides.
Okay.
I'll just say briefly that also the nonlinear behavior that we run into when we just sort of run harder perturbations is not quite as accurate, but it's still qualitatively the same. So this is looking quite promising. Also, critical coupling strength seems to be well captured by the normal form relative to the full model. So we have a promising normal form for power grid participants under natural assumptions. Really nice, they're low order polynomials. The interactions are given in terms of explicit state independent network Laplacian, and we have directly physically meaningful variables. We're currently studying how good the approximation really is and how much the various choices we had to make on the way towards this normal form matter. And then in the future, I think there's many open questions that open up when we have a new form that's sort of this Stewart-Landau-like form for power grids with a specified normal form of the coupling. I think this is sort of a very nice sort of also perspective shift for network dynamics community in general, to start from the physics of the coupling and then work towards the nodes rather than the other way around, which is often done. And I will just close briefly with an advertisement for the software that we're developing to help with a lot of these simulations also for realistic things. And if you're interested in running high performance network ODEs, then do get in touch and have a look at these packages. Thank you very much.
Thank you very much, Frank, for this very nice presentation, nice and interesting presentation. So we have time for maybe one quick question. Is there any question from the audience? I do not see any entry in our forum. Maybe Eckhart, as our co-chair, has.
Okay, I think now you can hear me, right?
Yes.
In this hierarchy of modeling approaches, which you mentioned, Frank, starting at a very basic level, a very simple level, and then with various extension, you can put in as much as you like and get to various more sophisticated levels. Would you say, or would you agree that it's useful first to start with the simple model, let's say chromotor with inertia, understand some basic principles, and then depending upon the specific question which you address, you can beef that up and put in more? Or is it a paradigm that
part of what we've been studying in the last 5-6 years, as you well know, is sort of how safe is it to do this, right? I mean, how much might you be misled by taking the simple model? And we know that, for example, just having a parameter like the losses, that still fits into the chromotor model, but having a parameter like the losses is small, which people used to do as a matter of fact, can mislead you heavily. Not having the voltage dynamics, this is something we found with Sabine Auer in paper. We found that not having the voltage dynamics in there can really mislead you heavily about the fixed points, about the stability of fixed points. So
maybe
I think this is not to say that we shouldn't start like that. I think we do. But my question was, in exploring this, is how do you go to the next step? And yeah, there is a modeling hierarchy that exists. And the modeling hierarchy exists for generators. It exists for sort of generators. You can look up a book and then you have a 10-order model, 8th-order model, 6th-order model, 4th-order model, 3rd-order model, 2nd-order model, and that's finally the inertial chromotor model.
We would
just go back up.
just advise that the plenary will start in a few minutes. I'm sorry.
Yeah,
I think what you said, Frank, about the voltage dynamics is important. That might become the new paradigm beyond comotor with inertia. And that's, by the way, also what Rico included in his transformation theory. So we can actually also transform that more sophisticated model, including voltage dynamics, into an adaptive network. That's maybe an interesting point to note.
Yeah, I saw that. I think that's excellent, because I think you and many others have looked at this, but again, if you just start from this sort of Schmiedendorf type, then you're maybe also missing some things, and we're always working with this sort of sine functions, cosine functions. Here, everything is polynomial, so that I also like quite a lot, but that's maybe also a matter of taste.
Okay, so I was advised by Mathieu that the plenary